¿verdad? El primero será Adrián Francisco Eduarte Rojas, quien es estudiante del posgrado de la Escuela de Física. Se graduó del bachillerato de Física de la Universidad de Costa Rica y además trabajó en caos en relatividad general y se graduará con honores de la maestría de Física de la UCR. Sin más, entonces, por favor, inicie, por favor, Adrián.
Muchas gracias. ¿Me da para compartir pantalla, por favor?
Por favor, que le den compartir de pantalla.
Listo.
Muchas gracias. A ver, acá está. Listo, todo el mundo puede verme.
Así es.
Okay. Well, good morning, everyone. My name is Adrián Francisco Eduarte Rojas, and today I will talk about the chaotic behavior of geodesics in space-time metrics with quadrupole moments. This is a research for my thesis, together with Francisco Frutos Alfaro and Rodrigo Carmoni Mendez. And we are from the School of Physics and the Space Research Center, also known as CINESPA, of the University of Costa Rica. Well, let me have a little introduction. So, in classical mechanics, the orbits around a stellar mass object are determined by Newton's laws of gravity, plus the Newton's three laws of motions. However, when the object, the gravitational source, is too massive, these laws are actually only an approximation. These laws, the Newton's laws, are not suitable for a complete description of gravity, especially in very strong gravitational fields, like the space-time surrounding a black hole or neutron stars, or even our own sun, when we are near enough. Only general relativity can describe and predict the motion of test particles or other objects around a massive compact object like a black hole. So, what happened in general relativity? In general relativity, the gravity is actually a description of the geometry of the space-time. What is the objective? What is the subject here? We need to have a metric. Here we have a very simple metric of a sphere. Here we have how to measure the distance between this point and this point. The length element is given by this simple law. This is very similar to Pythagoras. However, when we have these terms, we have the curvature of the space here. And general relativity makes no distinction between this object, the length element or the metric, with the gravity itself. So general relativity gives us a pseudo-Riemannian metric, and sometimes Riemannian metric depending on the signature description. So now what we have to do, we need to take a Lagrangian. But what is a Lagrangian? It's a function of the coordinates or general coordinates q and their respective velocities, and contains all the dynamical information of the system. So this function, the Lagrangian, will have the momentum of the system. It will have contained in some form the equations of motion, and give us a complete description of the system. With the Euler-Lagrange equations, permit us to write the path or the geodesic equation. But here we have another example or another view of the Lagrangian. If we have a manifold, which is the configuration space of the dynamical system given by the previous generalized coordinates Q. Therefore, here we have a function which is of the over the manifold, but also on this other set of variables. The set of respective velocities are another n independent coordinates from the original generalized coordinates. So we have two n independent coordinates. Therefore, the Lagrangian is a real valued function on the tangent bundle to Mn, or the manifold. So we have two views of the same object. To begin, we take a general metric in the Boyer-Lenquet coordinates and in the center of mass frame. Here we have a very general metric. So we have as a time part, a rotation part, and a space part. These functions v, w, x, y, and z are called potentials. And we need to be only functions of r and theta coordinates. Now we construct a Lagrangian using the reduced mass of the test particle. And we have an affine parameter. This affine parameter for massive objects could be the proper time. So we have the Lagrangian here. We need only to derive the length element with the affine parameter. This is also called the kinetic part of the Lagrangian, but it's the only part here. The upper dot means derivation respect lambda. And we define the conjugated momenta by this partial derivative of the Lagrangian respect the generalized velocities. And therefore we have four momenta. These two, the time and the phi part, are spatial ones because the original Lagrangian does not depend on the time or the phi angle. With the Euler-Lagrange equations, we could demonstrate that these two conjugated momenta are constants of motion. Here we have the conserved energy and the c component of the angular momentum. And we have two equations of first order. We could invert those equations and have the first two equations of motion. Note this, these equations of motion only depend on the constants of motion and the radial and as theta angle via the potentials, not the time or the phi angle. In order to find the remaining first differential equations, we need another formalism because the previous formalism with the Euler-Lagrange equations give us second order equations. So in order to describe a dynamical system, it's not suitable at this point. So we take another formalism called the Hamiltonian mechanics. We define the Hamiltonian via Legendre transform. And here it is. This part at least is evaluated in the velocities before. The Hamiltonian in the end will only depend in the coordinates and their respective momenta. And here we have the two Hamilton canonical equations. The Hamiltonian will be only a function of Q and the momenta P, but not in the velocities. via this equation. This equation here is not a change of coordinates, but it is a map from the tangent bundle to the cotangent bundle. This cotangent bundle is what we call the phase space in mechanics. An advantage of the Hamiltonian mechanics is that we have another constant of motion if the Lagrangian does not explicitly depend on the affine parameter. Then the Hamiltonian is a conserved quantity or a constant of motion. So we have the Hamiltonian here. Note this is Lagrangian, not the Hamiltonian at least. So if here we have the Hamiltonian in terms of the velocity, but we will have in the end in terms of the momenta. And this part is a constant of motion called epsilon. This epsilon is the conserved energy, but the spatial conserved energy. This is the rest energy of the system, or in our signature, minus the rest energy, which is equal to the rest mass of the massive particle. Also, we have the possibility to define an effective potential for this situation. Here we have a reduced version of our previous equation, this one here. And we have the effective potential here. These terms are very similar to conserved energy in classical mechanics. This equation here is a coupled first order equation and nonlinear because we have a second order, well, the square of the radial and angular parts. So this imposes us coupling between the initial conditions in the radial and angular part. One must be calculated and the other must be given free. For simplicity, we set the rest mass of the test particle equals 1. With the canonical equations of motion, we have the first 4 equations. Here it is, the previous 2 equations, and the other 2 first order equations of the velocities. And here we have the other 4 equations for the change of the momenta. Remember that these 2 equations were, well, and these momenta were constants of motion. Therefore, if we derive them respect the affine parameter, they will be equal to 0. And here we defined nearly an almost potential. This is ALM is nearly the potential that I showed you before. With the previous equations, we have a complete representation of the time-like geodesic and the phase portrait or phase space surrounding a compact rotating object like white dwarfs, neutron stars, or black holes. We only need the parameters of the metric like the mass, the z component, the angular momentum, the energy of the system, and the spin parameter, and the mass per dipole moment if necessary. We also need the initial conditions to solve the equations of motion, the previous set of equations. So we have the complete description here of our dynamical system. Now we need a metric. Well, the configuration space of this dynamical system for a given metric like the Kerr metric or the Kerr-like metric could have harmonic and chaotic behavior depending on the initial conditions and the parameters of the metric. We could not have only the perihelion precession, but also the plane precession in the presence of strong gravitational fields like the black holes or neutron star or white dwarfs or even our sun if we are nearly enough. But we need to be extremely near to the sun. So here is the Kerr-like metric, our metric here, and the subject of our investigation. The Kerr-like metric is a perturbed version of the original Kerr metric via a quadrupole mass moment. So what is the Kerr metric? The Kerr metric represents a perfect sphere, well, the spacetime surrounding a perfect sphere, which is rotating. The Kerr-like metric via the quadrupole mass moment represents a slightly deformed object, which is egg-shaped, and the spacetime is perturbed by that loss of symmetry. So we have the potentials of that metric and the auxiliary functions. Here, this term Q is the mass quadrupole moment, and P are the the polynomials of the are polynomials, spatial polynomials. So we have here the auxiliary functions. There are two important theorems that we need to characterize the evolution of the geodesic. Both theorems play a central role in Hamiltonian system perturbed by small parameters. Our parameter here, Q, is actually small. So this is the perturbation of the original Kerr system. When we set Q equals 0, we have the original non-deformed spherical object. Both theorems, these two theorems are the characterization of the chaotic behavior. The first, we have the Kolmogorov-Arnold-Moser, also known as CAM theorem, that says that if the bounded motion of an integrable Hamiltonian H0, the original Kerr system, is perturbed by a small change of the Hamiltonian that makes it not integrable in the total Hamiltonian. Here is the total. And if the next two conditions are satisfied, firstly, the perturbation is small, and the second, that the frequencies of the original are incommensurable, then the motion will remain bounded to an n torus, except for a negligible set of initial conditions resulting in a meandering path over the surface energy. The second theorem is the Poincaré-Birkhoff, and states that from the infinitely many periodic orbits in a resonant torus of the integral system, only an even number survive in the perturbed system. Moreover, half of these surviving periodic orbits are stable and the other half are unstable. So what we have here, one theorem says us that from the original theory, and when we perturb it, the new theory will be slightly deformed. Only a few of them will be broken. The Poincaré-Birkhoff tell us how they are broken. And we have most of the orbits will survive and they will be still confined to a torus. However, it's very slightly deformed torus. Although, on the other hand, we have the Poincaré-Birkhoff, and this tells us that we will have new structures in the phase space, as we will see later. So we have an example of a very simple torus. Here we have the frequency in the radial part and the frequency in the angle part, and how a particle is bounded to a torus. However, this torus is not in the configuration space or the space of the coordinates. Is in the phase space. This is very important because we will not see a torus here. So here we have a very simple example of a particle bounded to the previous set of equations. This is the numerical output of one particle, and we will see the perihelion precession and the plane precession of the orbit. And this is for a very simple case, for Q equals 0, the original Kerr system. So at the center here, we will have our compact object, like a black hole or a neutron star or a white dwarf or other compact object. Now we will use the same parameters of mass, angular momentum, spin, and mass, but we will change the mass and we will take the mass quadrupole moment, but change a little the initial conditions to construct a Poincare section. Here it is, a Poincare section for Q equals 0. And this is a very simple Poincare section. Here we have nothing here because those orbits here in this white part are unstable. They will fall to a black hole or the event horizon or to the compact object. They will be attracted because of the strong gravity. We are very near to the object. These ellipses here are one orbit. This is one orbit, this is another, this is another, and this is another. And we will see here that there are no structures besides these ellipses. They are completely ellipses. This part is known as the main island of stability. And the frontier between the white part and the main island of stability is known as the last stable orbit. This Poincare section is constructed via the radial momentum and the respective radial coordinate. And the Poincare sections contains all the dynamical information of the system. Now, what we will have to do? We increase the mass quadrupole moment, the perturbation parameter. When we increase this parameter, we see that many of these orbits are confined to torus in the phase space. They will be broken. We have now structures here and many structures when we increase a little the Q parameter, the mass quadrupole moment. Here we have, for example, a hyperbolic point. As we will see, this point is very similar to a hyperbola, and this is the hyperbolic point. Here we have small islands here, here, here. We will have islands here in these white parts, and here. We don't see them because I set the simulator only over this radial p sub r equals 0, but this is enough to see many structures. There is another hyperbolic point. These islands are also known as Birkhoff Islands or resonance. And here we have a structure here and small islands surrounding them and small islands here too. These islands here, here, and here are called satellite islands. We will see them in a moment. Here we have, this is an island, island surrounding this island here. This is not the main island of stability. This is a resonance. And these small islands here are our satellites. And we will have in this region and in this region scatter points. These scatter points are very important because they are the chaotic orbits. The tori was broken here, and we have a sea of chaos surrounding a very small island of stability, but not the main island of stability. Also, the last stable orbit is now undefined because we don't have a clearly frontier between this part and the main island stability. For Q equals 0, we have the hyperbolic points and a small Birkhoff change of islands here. Here we have the stable part the stable part only have an island here, but the orbits here are very stable, nearly the integrable orbits, but they are not integrable, only stable. For Q equals 0.7, we have many new structures. Here we have the same island and new islands here and new islands here, second order islands or satellite islands, many scatter points, a sea of scatter points for all this part. Another set of second order islands and the hyperbolic points. This hyperbolic point is very special because this part separates the chaotic and very unstable part from the stable part. Here it is. Also, well, if we set enough zoom here, we will see that there is actually no hyperbolic points. Actually, the hyperbolic points are composed by many small islands. Well, now we have to characterize this previous behavior. And we have a powerful tool to do that, the rotation number. The rotation number is defined as the ratio of the frequencies of the radial part and the Z angle part. This is called the resonance when the rotation number is a rational number and corresponds to an island in the Poincaré section. Moreover, when the rotation number is taken to be a function of the initial radial distance, then the rotation number will be constant along the extension of this island. So for this extension, the rotation number will be constant. For this part, it will not be constant. In the regular part, it will be an increasing value. But when we will have spatial structures like this one, we will have constant part, and with the hyperbolic point, we will have a discontinuity or a jump. Yes. So the hyperbolic points represents a jump in the rotation number. And when we have the chaotic part, the rotation number will be nearly undefined. It will oscillate extremely fast in the chaotic region. So the rotation number is a powerful test to identify and classify structures in the Poincaré section. Calculating the rotation number by definition is actually difficult. With this part, we'll have to do Fourier analysis or something else, and this is not suitable for us because this Poincaré section was obtained via numerical analysis because the original Kerr system is not integrable. The Kerr-like system is not integrable. The original Kerr system is integrable. So this definition is extremely difficult. So we have to do another algorithm to calculate the rotation number. And this algorithm is actually very simple. We need firstly to identify the center of the main island instability. We call it U sub 0. Secondly, we calculate the angle between 2 points in the Poincaré section, these 2 consecutive points. The position of the Poincaré section points are calculated using U sub 0 as a reference. And here is a simple formula. This limit is actually not necessary to be taken into infinity, but it is necessary in the end in order to reduce the noise in the calculation, because we have to do numerical analysis. Now we construct the rotation number along the piece of r equals 0 axis. then the chaotic regions could be detected. So, for example, here, we take the rotation number along this axis for initial radial values, for all the initial radial values. Oh, sorry. So here it is, a sketch. We have the main island stability. We have the center. We will have the two consecutive points. One point is here and later jumps to here. This point will not be here nor here. It will jump. This is an example of 2/5 resonance. And this is the angle that we take. Here it is in a true Poincare section. The center of the main island of stability. Now, the chaotic behavior is found to be dictated by another phenomenon, the stickiness. The chaotic orbits will remain attached to stable ones for a long period of time before they become divergent, and many of those orbits will be attracted to the event horizon of the compact object. So here we have an example for t equals 0.1. Here it is, the Poincare section. Here it is, an island, and this part is constant for the rotation number. Here we have a hyperbolic point, and we'll have a small jump here, another hyperbolic point, and a small jump here, another island here, and the constant part. Here we have a very tiny resonance in this point, and we see here that the rotation number oscillates very fast in this region. This is a small chaotic region. For this part is regular orbits, not chaotic ones. And the islands, we could see their respective rotation number. Here, for example, 2/9, 2/27, and 6/29. Those are resonance. For Q equals 0.3, we have the structure here. This island or this resonance is 2/9. And here we have a very small 6/25. The previous 6/29 disappears, but arises this another resonance. Here another resonance, but we didn't calculate it. For Q equals 0.5, here we have it. The 6/25 survives, and we have 2/9. The chaotic orbit here, the satellite is constant here. Between this part, this satellite, and this first order island, we have a very tiny chaotic region. Also here, we have another chaotic region here between this part and this hyperbolic point. So here we have a chaotic region, our new 6/25, and a very small chaotic region here that ends with this hyperbolic point. Now this part is completely stable. Here we have for Q equals 0.7, a new resonance here, 9/37, a chaotic region, and a chaotic region, and very little stable region. Later, a chaotic region here, and the stable region here, always with a hyperbolic point that signals the end of the chaotic part. Here we have for Q equals 0.9, the same structures here survives, but this is now a chaotic part. In the previous, we have a stable part. And here we have the, for Q equals 0.9, assumed in the rotation number. Here we have it. Here it is, another sum. And here it is, the radial part over the time in the chaotic part. We set it two orbits extremely nearly from one another. They are nearly indistinguishable for low t, but when we increase the time, they become divergent. And this is a very tiny time. They diverge for a larger time. So, some remarks and the future work. In the case of Kerr, for Q equals 0, it is easy to obtain orbits that do not fall into a black hole, but for Q equals 0, different from 0, the tori near the event horizon break, and we find the chaotic orbits that we see in the previous slices that fall to the event horizon. Some orbits remain stable, but chaotic. In order to study chaos present in the geodesics, we use the Poincare section and the rotation number near the event horizon. The difference between the different quadrupole moments have different behavior. The island positions change with the quadrupole moment, and some resonance are destroyed and other arises. And the stickiness phenomenon is extremely important to study this chaotic geodesics, because we need to do it for a long time of simulations. Now, for our future work, it is necessary to compare with other metrics like the Quevedo-Machoun metric, Hartle-Thorne, or Mann-Kononikoff metrics. And here we have a few references of our work. So if there are any questions, you could do it in Spanish.
Bueno, Adrián, muy bien. Yo creo que todos los que estábamos acá en esa sesión hablamos español, entonces yo creo que
bueno.
no había problema en que les pusiera en español, ¿verdad? Bueno, ahora en cuanto a las preguntas, yo tengo una. ¿Cuál es la importancia de este trabajo suyo?
Bueno, tenemos varias cosas. Primero, ¿dónde la dejé? También Ronald subió la mano y ahorita voy. Bueno, tenemos muchas métricas que pueden simular, bueno, que pueden modelar el espacio-tiempo alrededor de un objeto compacto. La métrica de Kerr ha sido muy buena, sin embargo es un objeto, digamos, muy idealizado. Es una esfera perfecta que está girando. Esa esfera perfecta sabemos de que no se da, no hay un cuerpo rígido, lo suficientemente rígido en la naturaleza que se da. En el momento en que uno gira, y en especial cuando gira más y más rápido, se va deformando un poquito. En especial con cuerpos tan grandes. Nuestro propio Sol se parece mucho a una esfera, pero él está ligeramente deformado. La Tierra tiene forma también de huevo. Entonces, ese es un detalle muy importante. Las métricas idealizadas no son exactamente físicas, aunque son una muy buena aproximación. Nuestra métrica, o sea, bueno, la métrica que usted propuso, la métrica tipo Kerr, tiene esa deformación, representa un objeto más real. Es una métrica, de hecho, bastante simple. Yo les menciono aquí esas otras métricas, pero estas otras métricas, Quevedo-Machoun, Hartle-Thorne y Mann-Kononikoff, son ligeramente más complicadas que la de tipo Kerr. O sea, las expresiones son mucho más largas. Esta es una métrica con una expresión relativamente sencilla de incluir en una computadora y poderlas poner a simular. Además, que es una métrica que salió, como se lo sabe muy bien, muy recientemente. Entonces, es una expansión al trabajo de este campo.
Está bien, sí, pero yo lo que me refería es en cuanto a las ondas
Bueno, gravitacionales. Bueno, hemos estado leyendo papers que nos dicen que las ondas gravitacionales contienen mucha información de el espacio de fases. El espacio de fases dado por esto se va a reflejar en las ondas gravitacionales directamente. Entonces, una onda gravitacional puede transmitir información acerca de las regiones caóticas que existen. Podemos llegar a comparar directamente con algún resultado en un futuro. O sea, mientras más datos recibamos de ondas gravitacionales, más fácil podremos ver si existen de verdad estas estructuras en el espacio de fases.
Bien, muy bien. Ronald Zúñiga tiene preguntas también, por favor.
Hola Francisco, hola Adrián. En
Hola,
nombre
buenos
del
días.
comité organizador, de hecho, agradecerles al doctor Francisco Frutos por colaborarnos con esta sesión tan bella de física hace poquito, pero me encanta, me apasiona mucho. Y gracias a Adrián por tan bella presentación. La verdad es que es una presentación muy bonita, muy, muy puntual de sus resultados y lo que sí noto es que hay un sabor de mucha geometría y eso sí me gusta bastante. Hay bastante geometría en el trabajo que realiza Adrián y aquí justamente cuando realiza la pregunta del doctor Francisco de las ondas gravitacionales y estos cambios de fase en el comportamiento caótico, en geometría esas superficies que estaba mencionando Adrián, hyperbolic surfaces y demás, es lo que llamamos submanifolds, critical submanifolds, subvariedades críticas de la variedad grande, ¿verdad? Eso es, desde la parte matemática, pues me da mucho gusto conocer, llegar a ver aplicaciones de lo que es geometría en algo tan nuestro, ¿verdad? Tan cotidiano. Es bastante rico. De nuevo, agradecerles por la presentación y estamos a la orden. Gracias, Adrián. Gracias, Francisco.
Gracias, Ronald.